Good morning, good afternoon, wherever you are in the world. Welcome to the Romax Technology Advanced Planetary Gear Sideband Analysis using Simulation Software webinar. Thank you for joining. I'm Rahini Sayal, Romax Marketing Campaign Manager, and the presenter today is Dr. Michael Platten, Romax NVH Specialist and Product Manager for Dynamics at Romax Technology. The presentation today will last approximately 45 minutes with a 10-minute Q&A session. Let's get started. I'll now hand over to Michael and let him go full overview of the webinar.
Hello everybody, thank you Rahini for the introduction. Let's get straight down to it. Many of you will have already attended the first two webinars in this series. This is the third one in the series with the overall aim of showing you what we at Romax can do for you in terms of NVH, but also in general understanding NVH problems, fixing NVH problems and so on, in particular looking for reducing prototyping, reducing development time and providing higher quality designs right first time. As I said, this is part 3. We've already had an overview of gear whine theory from me 2 weeks ago, and then Adam presented last week some in-depth case studies in preventing and solving problems. Part 4, still we don't have a date for that yet, but it's likely to be sometime in the next few weeks, so please keep an eye out on your either on our website, or if you subscribe to our marketing emails, then you will receive information about that. But today we're looking specifically at gear whine and sidebands in planetary gears. So what we're going to look at today, I'm going to give a brief overview of gear whine in planetary gears, and then look in particular at the topic of sidebands, which are a very important property of planetary gear noise. And we'll look at how we can simulate planetary gear whine behavior, and then we'll finish off with a case study looking at the effects of manufacturing variability on gear whine sidebands, and then finally finish up with a quick summary and the Q&A session at the end. So for those of you that weren't, and for those of you that were but have forgotten, I'll just give a very quick overview about transmission error and gear whine that we saw in the first webinar, just to get us started, and then we'll move on to the details about planetary gears. So gear whine noise is caused by transmission error, and transmission error is caused by imperfect transfer of motion by gears. So if we have an ideal gear and the driving gear moves at a constant speed with respect to time, then the driven gear will also move at a constant speed. But in the real world, that never really happens. In the real world, even if the driving gear is moving at a constant speed, there will be some fluctuation in the speed of the driven gear. And this is caused by variation in stiffness of the gear mesh and various other things which displace the gear mesh. And that resulting displacement is what we call the transmission error, and that is the source of gear whine noise, because that then causes vibrations in the rest of the system, starting at the gear mesh, transferred through the rest of the system, where it can be transferred through other parts of the structure or radiated as noise. In terms of the things that contribute to TE, what are the causes of TE? There are 4 sort of fundamental things that leads to transmission error. The first is basically anything that makes a situation less than ideal. So, for example, in a real transmission, the transmission deflects and deforms under load, and that causes gears to misalign. Gear teeth themselves deform under load, and their contact behavior changes under load. There is variability in the manufacturing of gears, which is unavoidable. Obviously we can reduce it, but we can never avoid it. Similarly with the assembly of the gearbox itself, there is always variability. That again leads to less than perfect conditions. And also we actually design gears to be less than perfect. We deliberately put modifications to make gears not true involute gears to actually account for all these other effects, and in fact try and reduce transmission error. But all of these things combine together to affect the contact behavior, for example, the contact load distribution on the gear teeth, and ultimately lead to the transmission error. And as I said before, when the transmission error happens, then this leads to these fluctuating forces at the gear mesh, which can be transmitted through the gears, shafts, and bearings to the housing. The whole system vibrates and responds dynamically to that excitation. Vibration can be transmitted through the mounts of the gearbox to other parts of the structure, and can also be radiated as noise and heard that way. So that was just a very quick overview for those of you that missed the earlier webinars. Now we're going to get onto the topic of planetary gears in some more detail. So planetary gears usually comprise a sun gear, planet gears which are orbiting the sun, hence why they're called planet gears, and a ring gear. That's sort of really the simplest form of a planetary or epicyclic gear set. Not really shown here that clearly, but the planet gears are connected together and held in their circular positions by a planet carrier, but which can of course rotate should we allow it to rotate. There's usually 3 or more planet gears in these systems. There are specialist situations where there may not be. There may be only 1 or 2, but typically it's 3 or more. And the gears themselves, the planet gears, may not be equally spaced around the circle. Here they are 90 degrees apart, but that is not necessarily the case. In addition, you can have different combinations of these gears. So here we can transfer torque via the sun, from the sun via a planet to the ring, or vice versa. But equally, you can have pairs of planets in there, so it could go from the sun to the planet to another planet and then to the ring, for example. It's sometimes called reversing planetary gear sets. They can be combined in various combinations where more than one planetary gear set share one component, maybe the same carrier or the same sun or even the same ring. And you can combine various planetary gear sets together in series, typically in something like an automatic transmission or a wind turbine, either to produce larger ratio changes or to produce a variety of different ratios in the case of an automatic transmission. There are lots of applications for planetary gears. The most common ones that we deal with are automatic transmissions and wind turbines, but obviously at Romax we see a lot of other things as well, and that includes things like range changers in automotive and off-highway transmissions, hub reduction gearboxes in off-highway for agricultural and machinery and construction machinery and so on. Many CVT transmissions have planetary gear sets in them. But also things like power tools, electric motors in general often have gearboxes attached to them for general purpose that are planetary gear sets, and hybrid drivelines, famously the Toyota Prius of course has a planetary gear at the heart of it. And as I was cycling to work this morning, I suddenly remembered that my bicycle, the hub gears in my bicycle also are planetary gear sets, so they are very common things. One particularly important property of planetary gears is load sharing. So the torque is split between each of the planet gears when the system is under load and turning. In an ideal world, the torque in each gear and the power going through each planet gear would be the same. In reality, there are things that mean that isn't true. For example, the stiffness or compliance in each of those paths through the planetary gears may be different. There may be, again, manufacturing errors and tolerances, and we'll hear a lot about those in this presentation, that affect that. For example, you can see at the top here, position of the planet gears and where they're mounted in the planet carrier has a tolerance on it, and that can affect the load sharing. And also there will be different deflections of the system at different rotational positions, partly because of the flexibility of these components like the planet carrier. Flexibility, by the way, is not necessarily a bad thing, as I'll highlight later. Critically, this means that all these effects vary as the planet gear set rotates. So not only do we have different torque in different planet gears, but that torque varies as the planet carrier rotates relative to the other components, and also the misalignment in each of those gear meshes also varies as it rotates, and we need to be taking account of that, particularly when we're talking about the noise and vibration behavior. So in terms of gear whine in planetary gears, obviously as you can see there are several gears in mesh at the same time, and every single one of these gear meshes, 8 gear meshes in this case, all have the same tooth passing frequency, and each have their own individual transmission error. Each of these 8 meshes in this example each have their own transmission error, and depending on what we call the phasing of those transmission errors, they can either add up together if they are in phase. So here you can see 4 transmission errors in phase adding up to produce a large overall transmission error for the planetary gear set as a whole, or they can cancel out. They can be staggered, as you see here, and then here they tend to cancel out and produce less transmission error than a single gear pair would have on its own. And how this phasing is determined is based purely on the number of teeth in the gears, the number of planets, and the spacing of the planets, i.e. in our case 90 degrees in this example, but as it could be others, and obviously if you have different numbers of planets it will be different. So those 3 parameters fundamentally determine this mesh phasing and whether you get reinforcing transmission error or cancelling transmission error. There are different combinations of these parameters will give you different results. There are 3 examples here, 3 of the most common ones. In phase, which is equivalent to the picture over here, all the gears are at the same point in their meshing cycle at the same time, and this results in a larger torsional fluctuation of the system, because these transmission errors add up to give a combined torsional variation, illustrated by this red arrow, but radial forces are cancelled out. They're balanced in the radial direction. If we have sequentially phased, which is similar to what you see here, then we have the opposite situation. So now we have removed the rotational, the torques, and also in a helical gear you will get axial thrusts associated with that torque as well. Those torques will cancel, but now the radial components do not cancel, and you end up with a resulting overall radial excitation. Depending on planet spacing and so on, there are other things you can do. Another common one is counterphase, where you try to cancel both the torsional and the radial components. Obviously, you never get perfect cancellation, so there will always be some residual effect. But in general, people try to avoid this sort of design and stick to these two. Now, this isn't always possible, and in fact, it may be desirable to have this type of design in some situations, but we can come on to that a little bit later. In terms of this mesh phasing, obviously the aim of the designer is to choose tooth numbers and planet arrangements that minimize the overall excitation, whatever that may be, whether it's the torsional or the radial. But because the world is imperfect, we never get perfect cancellation. All the variabilities of manufacturing and assembly and so on, unequal load sharing between the planets, deflections of the gear set under load, etc., all lead to imperfect cancellation. So you never get as good as the ideal scenario, if you like. But another property of these is that as the gear set rotates and the loads change and the misalignments change, we get a variation of TE, variation in the transmission error. And this leads to modulation of the transmission error, and that's what causes our sidebands. So I mean modulation in the sense like in AM or FM radio, amplitude or frequency modulation. Typically TE is a mixture of those two types of modulation. The example that you can see down here shows an example of predominantly amplitude modulation. So we're looking at the transmission error for a planetary gear set across one entire revolution of that gear set, one revolution of the carrier. Each of these bumps here is the transmission error caused by one tooth pass, and obviously there are many tooth passes in the complete revolution. But what you can see is that here at this starting point, the transmission error, the amplitude of these bumps is quite large, whereas at this point in the cycle, the amplitude is quite small, and then they become large again. So that is similar to amplitude modulation. You can ignore this once per revolution part. That's not important from a noise point of view. We're just looking at the amplitudes here, here, and here. So that variation is what leads to sidebands. So why are they called sidebands? Well, if we take the signal and Fourier transform it, we'll find there's a component at the once per revolution frequency that you can see here, this rotation frequency, a large component. You can see it's dominating that graph. We're not interested in that from a noise point of view. It's pretty low frequency. Of course, we have the mesh frequency as well, although we don't always see the mesh frequency, as we'll see later. But typically, you will see some energy at the mesh frequency. But the modulation, when we do this Fourier transform, introduces these additional peaks called sidebands. Sidebands because they are bands of energy either side of the mesh frequency. I've just shown one in this schematic diagram. In reality, there will be a whole family of different sidebands, but often one or two sidebands will tend to dominate. I say it is possible for the mesh frequency to be almost non-existent and see only energy in the sidebands. Now, we talked about the phasing of the gear meshes. Sidebands also have phasing properties, and so different sidebands can also reinforce or cancel as well. But those phases are different from the phasing at the mesh frequency, and they're different from one sideband to another. So we also need to think about that when we're trying to predict these things. So where do these sidebands come from? How do they get into the transmission error? Well, there's three main sources of sidebands. The first kind are physical deviations from ideal component geometry, or component position. So this is things that are either errors in the manufacturing or within tolerance bands, or sometimes out of tolerance bands. There are also deflections of the system, either under torque load or other external loads. And these cause modulation of the transmission error, like we saw in the example on the previous slide. So those are modulations and sidebands that appear in the excitation signal for our gear whine, the TE. The second class are caused by variations in the modulation of the vibration response, and this is due to the fact that as the system rotates, the gear meshes move their position within the gearbox. and therefore the path from those gears to wherever you are measuring, whether that's an accelerometer on the housing, a microphone, or even your ears as you listen to the noise from the gearbox, that transfer path changes as the system rotates and the meshes move. And then the third type of sidebands are not strictly modulations in the true sense, but they come from the fact that some of these forces are rotating. So we have radial forces that are rotating, and they're in a moving reference frame because they are rotating. But we are measuring with an accelerometer, microphone, or by listening or whatever, we are measuring out the response in a fixed stationary reference frame. And what this means is that when we work out the maths of this, some of the exciting forces and moments shift in frequency because of that rotation, and some do not. And this is down to this change of coordinate system. So it's a mathematical effect rather than some physical deviation or error in the system. So we'll look at each of those in turn. In terms of physical deviations, we can divide them into categories of manufacturing and assembly deviations and operational deviations. So manufacturing deviations can be things like runout, eccentricity of components, as you can see here, which means we have a less than perfect system. There could also be a swash or a tilt on one of the components. Things like pitch errors, i.e. the spacing of gear teeth, are particularly important, especially in ring gears, where it's not as easy to manufacture accurate ring gears, internal gears, as it is to manufacture accurate external gears, and they're typically where the largest pitch errors occur. Other distortions of components like ovalization can become very important as well. They tend to show up actually rather as pitch error variations rather than an out of round, and that's where they have their most effect as tooth spacing errors. And things like the planets might have slightly different sizes. The pin positions we talked about maybe slightly out, even by a few microns, can all make a difference and affect the sideband behavior. Also, as the system is loaded, misalignments due through the loading of the torque, displacement due to gravity or other loads being applied from the outside of the gear set can affect and cause this kind of displacement as well, leading to the unequal load sharing. In something like an automatic transmission where you have components that are clutched or braked, either clutched to each other or braked to housing, then something like a run out can vary every time you engage that gear because you don't know what the run out will be at the point where a clutch clamps together. And so that means you might see a different set of sidebands in one time when you're in a particular gear state to when you're in another time when you're in the same gear state. It can vary each time. And when we're looking at very high speeds, we've got quite large inertias whizzing around here at high speeds, so you can get orbiting of components due to out of balance is another possible source of this kind of sideband. The second kind of sideband, the transfer path variation, these are the ones that affect modulate the response rather than the ones we've just seen which modulate the excitation. There's one very obvious reason why this happens. If as the system rotates, you can see here an example of the system in two different positions. When this gear is right, when this gear mesh is right underneath our sensor, it will register quite a high vibration. When it's further away, it will measure a lower vibration. But equally, it's actually a combination of all of the excitations coming from each of these gears. And as the system rotates, those paths between the excitation and the measurement point will change as it rotates, different phases, different amplitudes, and we will get modulation happening, a mixture of once per revolution and also maybe once per planet pass. And then the third kind are these coordinate transform sideband effects that come from the fact that we have a rotating excitation. So the forces are in a rotating reference frame, but the measurement is being performed in a stationary reference frame. And there are a number of different planetary arrangements where this can happen. The example shown here is where we have some unequally spaced gears that are in a counterphase condition, and we end up with a resulting radial force that spins round at the speed of the carrier. And I'm not going to go through the maths here, but you can work out the simple trigonometry. You can work out that if I just have this force, spin it round, I end up with two frequencies, one at mesh frequency minus the carrier frequency, and one at mesh frequency plus the carrier frequency, i.e. some sidebands. Other types only produce sidebands on one side of the mesh frequency. But in this case, these radial forces appear at sidebands either side of the mesh frequency. But this is only for the radial forces. The torsional forces and axial forces along the length of the shaft do not shift because they're not seen by the system as rotating. So we get a mixture of those two things. And one very important thing here is that these frequency shifts occur even if the system is perfect. We don't need any of these manufacturing errors. No defects are needed to generate them, although they do have an effect on them and also on the sound quality. But even if in a perfect system, you would still see this shift in frequency due to this effect, and therefore it's very important for us to consider. So to summarize those, then we've got the transmission error modulation, i.e. the excitation modulation from physical deviations. These typically are the most important, and the reason is because they actually create additional energy in the region of the mesh frequency, the part of the spectrum around the mesh frequency, so the mesh frequency and its sidebands. They do that by bringing energy up from the lower frequencies, the once per revolution frequencies and twice per revolution frequencies and so on, and they are heterodyned up to the region around the mesh frequency by the modulation. So they increase the overall amount of vibration and therefore noise around the mesh frequency. Type 2, which are those modulation of the response by the transfer path, are less important. You're not creating additional energy, you may be moving it around a bit. They also have a relatively small influence on the radiated noise in general. The type 3, those are changed from the rotating reference frame to the stationary reference frame. Again, these don't generate additional energy, but they do move it around, and they move it around significantly. Even, like I mentioned, in a perfect system, there could quite easily be a situation where you would see no vibration or noise at all at the mesh frequency. It would all be at one sideband or a pair of sidebands around the mesh frequency. And that has a significant effect on the sound quality, and obviously, therefore, you need to be able to understand that. How do we go about simulating this? Well, of course, the aim of simulation typically is to answer the question, will my design meet the noise target? And as with a lot of things with noise and vibration and dynamic problems in general, it's very difficult to answer this question at an early stage in the development process, because you need a really detailed model to be able to give you that level of prediction, if you like, of noise and vibration behavior. But we have a problem here, because if you remember, the things that most affect the sideband performance, that is the number of teeth, the number of planets, and the spacing of planets, are the very things that you want to be able to define very, very early on in your development process. So we need some kind of tool that we know it's not going to give us predictions of noise levels and things at an early phase, but we need some kind of tool which is going to give us qualitative information about the design, about which sidebands are likely to occur, which sidebands are most sensitive to which types of errors. We need that at that concept level, and I'll briefly show you an example of that when we look at the case study. But of course, once we do have a more detailed design, we can then go to a full dynamic simulation. We can construct a dynamic model, and we can use the Romax tools for actually produce quantitative predictions that we can compare with the targets. And we'll see in the case study again how we've managed to achieve some very good correlation. So this is the process for doing this simulation. You build your transmission model in Romax Designer. You then, and this is really critical, you need to add in the loads and the manufacturing variations that are causing these imperfections in the system. They don't naturally occur in the nominal system. We have to actually put them in. And you'll see exactly why this is very important when we see the case study. But they don't naturally occur. You need to tell the model there is an error in this component, there is an offset in this component, there is a run out in this component, and make sure those are in the model for it to be able to generate those type 1 sidebands. We then calculate the transmission error, typically for one revolution of the carrier with respect to the ring gear, although not always. And I say that like it's an easy thing. We'll see in a minute. It's not that easy. We have a lot to consider in calculating that TE, much less straightforward than the demo I gave in this webinar and the webinar 2 weeks ago. And we'll talk about that a little bit more in a minute. We then can, as we saw in the previous webinar, we can do the dynamic simulation, we can create the frequency domain model, get the mode shapes and natural frequencies and so on, apply those transmission error excitations, which include those type 1 sidebands, and predict the response on the housing. What we then have to do is we have to account for those type 3 sidebands as well, those frequency shifts due to the coordinate shift, and we've developed some new software capabilities that allow us to do just that and take account of those type 3 frequency shift effects. And then, of course, we've got the vibration on the housing, but often we're interested in the radiated noise, so we can export that housing vibration, put it through radiation simulation software to predict the noise radiation and the radiated gear whine. I mentioned about the difficulties in looking at transmission error in planetary gears. In our ordinary parallel gear sets, we can make some pretty good assumptions. You know, these aren't always true, but they most of the time these assumptions hold. Typically, the misalignment does not vary with the rotational position when we have parallel gear pairs. Typically also, in an average sense, the torque doesn't vary with rotation. And we can consider the behavior of one gear set of being independent of the behavior of the others in most cases. If we have a gear train, that's not really true, but in most cases that is the case. So that means that the gear geometry, a constant torque, and a misalignment that we work out from the system deflections of our model are the only inputs that we need to calculate the gear contact behavior and the transmission error. So once we have that information about gear geometry, the torque, and the misalignment, we can consider the contact behavior in isolation from the rest of the system. When we look at planetary gears, none of this is true. It's much more complicated. We have misalignment that varies with rotation. We have torque that varies with rotation. We have unequal load sharing. Each gear mesh transfers different torques. And also, we have all these very closely coupled gear meshes, and each of those interact with each other. So the misalignment on the mesh between the planet and the ring affects the misalignment in the mesh between the planet and the sun, for example. They all interact. And also the whole system changes as the system rotates because all the stiffness behavior changes because all the meshes are in a different position. And we need to consider all of these things simultaneously within the context of the whole system if we want to be able to predict this planetary gear TE. So you can see it's much more involved than the relatively simple contact analysis that we're able to do for parallel gear pairs. Up till recently, we could use our Romex Designer software to predict these sidebands coming from these type 1 effects, the physical deviations and the errors and so on. That's been in our software for some while. But recently we've extended this methodology with a new module that allows us to include the effects of these type 3 sidebands, these coordinate transform sidebands. It's, again, like much of the dynamic analysis within Romex Designer, it's frequency domain based, which means it's very fast to run. Now, just taking one step back a little bit, remember I said that there was a need to be able to understand sidebands at the concept level because we have to define these properties, these very basic properties of number of teeth on the gears, number of planets and spacing of planets. We need to decide this very early on, and we need some indication of what's going to happen early on. And we need that so we can predict which sidebands are likely to occur, to understand how sensitive those sidebands are to different types of manufacturing error. And we can do it by understanding what the expected phase of those gears and the meshing frequency and phasing of the gears at the sideband frequencies is going to be. And there's some relatively simple calculations that can be done to work that out. We've built this into a much more sophisticated tool that we use internally here at Romex for doing this kind of analysis, and you'll see a result of that in a moment when we look at the case study. We can work these out. What you see in front of you is actually just from a very simple spreadsheet for calculating those ideal phases. We can work out what the sideband phasing is likely to be, and from that we can understand what kind of errors are likely to cause those sidebands. So the table that you see here is from a gear set which actually has is one of these gear sets with additional planetary gears. So we go from Sun to inner planet IP to outer planet OP to a ring gear. And there are 3 inner planets and 3 outer planets. And we can calculate these phasings, and if we look at the mesh frequency, we see that we have phasings that are separated by 120 degrees. We have the sequential phasing. So we're looking at a gear set that in theory should cancel out torsional vibrations at the expense of a degree of residual radial vibration in the planetary gear set. And that's for both the inner planets and the outer planets, separated by 120 degrees. We can also calculate those phasings for the sidebands, and we can see for the first upper sideband, that's 1 carrier order above the mesh frequency. Again, we have sequential phasing, 120 degrees apart. Similarly, with the second lower sideband, that's 2 carrier orders below the mesh frequency, we have that. But for the first lower sideband and the second upper sideband, all the inner planets are in phase, all of the outer planets are in phase. All the inner planets in phase, all the outer planets in phase. So for these sidebands, we would expect this to generate quite significant torsional excitation if those sidebands do indeed appear and get excited. So we can make some design decisions early on because we can identify what sidebands we think are likely to occur, and based on whether they are first order or second order sidebands, we can look at which types of manufacturing error are likely to cause that sideband to be excited. So I'm now going to go through a case study on the effects of manufacturing variability on gear whine sidebands in a automatic transmission which has more than 8 forward speeds. This was a summary of a joint paper that I presented at the NAFEMS North America conference a few weeks ago with our colleagues at Ford Motor Company, a joint presentation. And the paper shows how we can predict sidebands using the Romax software and using our methods, and this is the most important part really, that including the effects of manufacturing variability is absolutely critical to making the correct design decisions, and it's very, very clear from the results you'll see in a second that we really, really need to include that manufacturing variability to get useful information about these predictions. But what we also show is we get very good correlation with measurement, and also that we can use those tools that I've just described in the early phase to get really good qualitative information about gear whine performance early in the design process to help us towards that right first time design. So the situation in this gearbox is like this. We've got 2 different competing designs for a planetary gear set. There are a number of gear sets in this gearbox. We're just looking at one of them, and we're comparing 2 different designs. One is a 3-planet design, which has reinforcing mesh phases, i.e. the torques add up, and one is a cancelling design, a 4-planet design that nominally cancels mesh phases. And generally, in most situations, particularly in this type of transmission, we expect cancelling designs to be quieter than reinforcing designs because they tend to be more sensitive to torsional vibrations than radial vibrations. What this slide shows is the results of the analysis and a comparison with the test data. So the test data that you can see for both the 3-planet and the 4-planet designs are these solid lines here, and you can see this behavior. We're looking at sound pressure level, so radiated noise, and we're looking at sound pressure level not just at the mesh frequency, but the mesh frequency and all the sideband frequencies as well, all added together into one result. The dotted line here shows the results of the simulation, and this is the results of the simulation if we do not include the manufacturing variability. The critical ones in this case are pitch errors on the ring gear and run out of the carrier with respect to the ring gear. And you can see that if we were to take a prediction based on that simulation, we would see that the red line here, the 4-planet design, is much, much better by more than 10 dB in some areas, much, much better than the blue dotted line, which is the 3-planet design. So our engineering decision would be, right, let's use the 3-planet design then. But you'd be making the wrong decision because you're not including the manufacturing variability. The dashed lines here, the red and blue dashed lines, show the results of the simulation when we do include those errors of pitch errors and run out of the carrier with respect to the ring gear. And you can see when we do include those errors, we get, there's 2 main things about this. First of all, is it matches the test data very, very well for such a complex system, including all that sideband behavior. And the second thing is that there is, within the boundaries of error of both the analysis and the measurement, there is no difference between the 3-planet and the 4-planet design. They produced very, very similar results. And of course, that's exactly what the test data shows. There is no difference. So we expect a 4-planet design to be much better. In fact, it's not. Once we include the manufacturing variability, we see no improvement whatsoever. There are plenty of reasons for this, which I don't have time to go into today, but it just shows the importance of including those manufacturing errors in that calculation. So we know we can get nice accurate predictions of radiated noise provided we include the manufacturing variability in our analysis. But what about the sidebands? The color map on the background is the order spectrum measured from test. So we're looking at the different vibration orders, rotational orders along this axis and versus speed on this axis, and the color represents radiated noise measured by microphone. This is for the 4-planet design, and this is one of these examples I said where you don't see the mesh frequency at all. The gear mesh frequency is here, in this order here, and you can see there's there's a little bit of red there, but almost all of the energy has been moved to sidebands, and this is a mixture of the contribution of the errors and also the type 3 effect of the coordinate going from rotational to stationary coordinate frame. Now, on top of that, we have superimposed 2 different sets of results. The lower result here is the prediction from our fully detailed dynamic simulation with a fully detailed model using all our sideband tools, all our transmission error prediction tools, and so on. And we see that we predict where the dominant sidebands are going to be. We get those pretty much spot on. The relative amplitude that you can see on this picture, but we've already seen on the previous picture that actually the true amplitude is predicted correctly as well, because we got such good correlation. The top line here is from a concept-based analysis, which uses only those very basic parameters we talked about before, and those ideal mesh phasings, combined with a few other tricks and so on, to take account of the type 2 and the type 3 sidebands. But you can see from this basic analysis, we also predict the correct distribution of sidebands. Now here we're not predicting absolute noise levels or absolute vibration levels, but we are predicting which sidebands are likely to occur, and the test data agrees with that. What we can also do here is look at sensitivity to different types of errors. So we can change the types of errors that we're inputting, the amount of those errors that we're inputting into there, and again get in a relative sense, an idea of how sensitive each of those parameters is in terms of their sideband behavior. So we've got those two tools we were looking for. We've got those absolute predictions from our detailed analysis, but we also have this concept tool that allows us to look at those decisions very early on, which is exactly when they need to be made, because those fundamental parameters of number of gear teeth, number of planets, and spacing of planets have to happen right at the start. Just to conclude on the case study, so just to re-emphasize, we've successfully predicted the noise and vibration response of this transmission, including the sideband behavior. We've got excellent correlation with the measurements on the real transmission. We've also shown that it is absolutely critical to include the effect of manufacturing variability, and if you do not, you're going to be making incorrect design decisions, and that was illustrated very, very clearly in those results. We've also seen that we've got the correct distribution of vibration energy between the different sidebands, and we've predicted that both with our fully detailed model and also with a concept model. So that means we can predict those behavior early on, at least qualitatively in the development process, when we are defining those critical parameters. And the value, of course, is relatively obvious, but is worth saying. This is supporting the engineer to make those critical design decisions as early on in the process as possible. It's allowing us to see if a design will meet noise targets before we get to the prototyping phase. It allows us to identify the sensitivity of a particular design to different manufacturing variabilities. That allows us to identify where perhaps we need to tighten tolerances, where we can maybe relax tolerances, but whatever, to be able to set our tolerances and manufacturing capabilities accordingly. And of course, as a result of that, we're looking at reduced development times and costs and a higher quality product at the end of the day. So just before we move on to the Q&A, I just wanted to leave you with a few tips and tricks about designing quiet planetary gears. Obviously, this is a huge topic, and these are very general things to say here, but they're important things to take note of. And the first obvious thing is to choose tooth numbers, planet numbers, and planet spacing that give you the cancellation that you need. So if you have a transmission or a design that's sensitive to torsional vibrations, then you want to cancel the torsional excitations, obvious. Similarly with the radial. If it's sensitive to radial vibrations, then try to cancel the radial forces. And there is the option, although they do restrict the types of design you can have, but of attempting to cancel both of those things at the same time. Of course, as I said, we never get perfect cancellation anyway, so it's still important, just as it was with the normal parallel gear sets that we talked about in the first webinar, to minimize the TE at the individual gear meshes, optimize the microgeometry, optimize the contact ratios and so on, just as before, to give as small a TE as possible across the required load range, so that when there isn't perfect cancellation, we are still reducing the TE. Another thing we want to do is try to maintain equal load sharing between the planets, because that also helps us to get good cancellation when we've designed good cancellation, and it also helps us to reduce potential sidebands. One way in which you should try and do that is by avoiding the over-constraining of all parts of the planetary gear system, so the Sun, the planet carrier, and the ring. We don't want those all radially constrained, so they're all held rigid, if at all possible. We want a bit of flexibility in the system and allowable movement to allow it to deflect when it is under stress from these manufacturing errors and system deflections and so on. And the best way of doing that also is to have 3 planet gears. That's not always possible. You might need more planet gears to take all the load that you need. You might need more than 3 planet gears to give you the cancellations that you want, but 3 planet gear sets tend to have the best load sharing between the planets. And of course, as we've seen from the case study, you need to simulate the behavior to understand the effects of manufacturing variability on noise performance. If you simulate the nominal design, perfect design, no errors, you will more than likely get the wrong answer. You'll very accurately simulate the perfect design, but you never get the perfect design. And these things can be very, very sensitive to these errors. So just a quick summary, we've seen that predicting gear whine in these planetary gear systems is much more complex than parallel gears. Many factors need to be taken into consideration when we are doing this kind of simulation and prediction. We've seen that sidebands are important in understanding the noise and vibration behavior of these gear sets, and in fact are critical to understanding them. Just to re-emphasize this point, because it is so important, we must understand the manufacturing variability and how that affects both the noise at the gear mesh frequency and at the sidebands, and is critical to our successful design. And we've also seen the importance, because of these fundamental nature of the parameters that affect this, we need to consider the sideband behavior very, very early on in the design and development process. And hopefully you'll agree with me that we've seen that our tools here at Romax and our expertise, we have all those things that you need to ensure high quality, right first time designs for planetary gear systems. So that's the end of my presentation. Thank you very much for listening. This webinar and the other webinars in this series will soon be available on our website for you to view at your leisure. Of course, you can contact us with more questions if your question doesn't get answered during this session. One little advert for our user forums. We'll be having user forums this year in India this month, and in the rest of the world later on in September and October, where you can come and meet Romax experts, meet senior Romax people. You'll see presentations from customers, you'll see presentations from people at Romax, and some very interesting keynote addresses as well. So again, please look at our website for that. I'm definitely going to the two ones in India, in Pune and Chennai. Likely also be in Detroit as well later in the year. So you can talk to me, or of course any of the other Romax people then, or feel free to contact your local Romax representatives in the meantime. So I'm now going to have a look at what questions have come up. Okay, so we've got a couple of questions. Thank you for those. The first one is, what kinds of manufacturing error have you considered in your case study? So in this case, in particular, we've looked at the pitch errors on the ring gear. Of course, the ring gear being the gear in the planetary gear set that is hardest to accurately manufacture, and based on a sensitivity analysis, those are the ones that showed they had the largest impact. Because this was an existing transmission, we were able to use measured pitch errors from this specific ring gear, but obviously you will have metrology information from your manufacturing processes about typical ring gear pitch error behavior. In this particular case, there was quite a significant ovalization as well, a fat part to the pitch error, so it wasn't just a once per revolution, there was a twice per revolution component to that pitch error as well, and that's also very, very common in ring gears. The other question is, how much contribution of type 3 coordinate transformation in your case study dynamic response compared with type 1? Well, it really is a mixture. The majority of the sideband behavior comes from the type 1, because those are the ones that add additional energy in. The type 3 sidebands just move energy around between different sidebands and adjacent sidebands. So some of the sideband energy largely comes from the type 1, but they will be adjusted and moved around by the type 3. So if we go back to this figure, we would expect to see some energy here at the mesh frequency. There is hardly any here at all. It's all been moved to various sidebands by a mixture of type 3 and type 1, but the overall energy contribution, the overall sideband behavior here is coming predominantly from the type 1 sidebands. There's a question here. Many authors claim that a pattern where the sidebands are higher than the gear mesh frequency on a spectrum suggests that the gearbox won't run. Do you have any idea why many authors claim that? No, is the answer to that. It is quite possible from the type 3 effect alone, without any manufacturing errors, just from that coordinate transform effect, that you can end up with no energy at the mesh frequency and all the energy moved up one order to the order above. The modulation sidebands tend to cause symmetric sidebands, so you get equal numbers of sidebands below and above. And the follow-up question on that is, do they suggest a particular type of error, those sidebands? Not really. As I say, typically type 1 sidebands will cause an equal distribution from one side to the other, above, whether they are above or below. Of course, there may be resonances that are missed by the lower sidebands but are hit by the upper sidebands, in which case you may see a higher response in that case. But if you see a large asymmetry in the sidebands, it's usually because of the type 3 effect rather than the type 1 effect. From the concept tool, can we find a design which will cancel main mesh as well as sidebands for given errors? Yes, you can. You can look for those. Typically, you can't do that with 3 planets. You need at least 4 planets to do that. Typically, it's done with 4 planets. And usually, it also means having unequally spaced planets. Some people even try to move just 1 planet so that they're not even symmetric, and then you have to obviously look very carefully at the balancing of the planet carrier when you do that. But there are designs that nominally will give you cancelling of both radial and torsional forces. But remember, it's never perfect cancellation. As soon as we put in errors as well, we tend to destroy the cancellation, and also the putting in errors also changes the phasing. In our detailed models, our detailed dynamic simulation, when we look at the phasing of the TE, although they nominally would be, for example, one of the examples we showed was 120 degrees apart or 90 degrees apart, sometimes they shift by a considerable 10, 20 degrees away from that in terms of their phasing. So you never get exactly what you want. Also, you are restricting the different designs that you can come up with by only having 4 planets, by having 4 planets instead of 3, and so on, and having to unequally space planets. I think that's probably all we have time for now. Thank you very much for your questions. Thank you for your attention. As I say, recording of this webinar will be available on our website soon, and you'll be sent out an email to let you know when that's the case. Go to the website for information about more webinars. Please also consider coming to one of our user conferences, and we would love as many of our users as possible to be presenting their own studies at our user conferences as well. That's what people come to our user conferences to see. They don't want to hear me going on about sidebands. Well, some people do, but they want to hear what other users are doing. So if you have an interesting topic that you want to present, then please talk to your local representative about that. And in any case, please consider coming to one of our global forums. So thank you all, and hope to see you soon.